Is that Amelia? 10 points.
Oh my gosh, is she not gonna stop?
Oh!
Now let's take a closer look at what happened. Just like Maddie and Amelia's collision, one car is at rest while the other is moving.
But how does this tie into physics? Today we're looking at impulse and conservation of momentum, which is Unit 5 in AP Physics. So first, let's talk about inelastic and elastic collisions. Inelastic collisions are collisions between objects in which kinetic energy is not conserved. This is because some of the energy transfers to thermal energy. Elastic collisions are collisions which energy is conserved. Perfectly inelastic collisions are collisions in which objects stick together. Our car collision is an example of an inelastic collision. So what role does momentum play in these collisions? Well, let's look at what momentum is. Momentum is a vector quantity. External forces affect momentum. And finally, in physics, momentum is normally demonstrated by P. So some equations for momentum. Momentum equals mass times velocity. Change in momentum is force times change in time. And finally, let's look at the conservation of momentum equation. So this is the equation here, and we're going to take a closer look at this with Maddie's example. And here is a slightly different version of the conservation of momentum for perfectly inelastic collisions. So what does this mean in terms of collisions? Let's take it over to Maddie.
Mario's 2,575 kilogram car crashes into a sleeping mater who weighs 825 kilograms. They move off together at 8.5 meters per second. Assuming no friction with the ground, find Mario's initial speed. So because they move off together, this is going to be an inelastic collision. So the first thing we should do is list our givens. So Mario's car weight is going to be m1, and Mater's car weight is going to be m2. And like we said, since this is an inelastic collision, this means that kinetic energy will not be conserved. Velocity 1 initial is going to be Mario's initial velocity, which is what we're trying to find, so we're going to label that with a question mark for now. Velocity 2 initial is going to be Mater's velocity, and since he's at rest, that's going to be 0. And then we know that they move off together at 8.5 meters per second, so that is going to be both of their final velocities. So the formula we're going to use is P equals m times v. And since we have two cars who have two different initial velocities and in the same final velocity, we're going to use m1 times v1 initial plus m2 times v2 initial is going to be equal to, in parentheses, m1 plus m2 times velocity final. And then we're just going to plug and chug these numbers. So after multiplying all this out and solving for velocity initial, we're going to get 11 meters per second. And this is going to be Mario's initial speed. So as we said, kinetic energy is not going to be conserved since this is an inelastic collision. So we're going to calculate how much kinetic energy is actually lost during it. So the first thing we need to do is find out the kinetic energy total before the collision. So we're going to label this as kinetic energy 1 plus kinetic energy 2. And the formula for kinetic energy is 1/2 mass times velocity squared. And since there's two, we're going to add them together. And then we're going to plug and chug, and in 1/2 of this, we're going to put Mario's mass and initial velocity, which we found previously in the problem, plus Mater's mass and his initial velocity. But since his initial velocity is 0, that side is going to cancel out. And then after calculating it together, we get that the total kinetic energy is 155,787.5 joules. And then now we're going to do the kinetic energy after the collision so we can see how much is lost. So to do this one, we're going to add the kinetic energy 1 plus the kinetic energy 2 plus the lost amount, and we're just going to label that as lost. So after the collision, similar to the original equation we used, they both have the same velocity in the final velocity. So we're just going to add together the masses, divide them by 2, and multiply that by the square of 8.5. And then we're going to add loss to that. And then after calculating that, we can find out that this amount is 122,825 joules. So then we're going to set these equal to each other. So we're going to have 155,787.5 joules is equal to 122,825 joules plus the lost amount. And then after subtracting these, the lost amount is 32962.5 joules. So obviously that's a pretty big number, so we're going to find out the percentage that is lost. So by doing that, we're just going to divide the amount lost over the total amount and multiply that by 100. And then after doing this math, we find out that 21% of kinetic energy is lost.